All right, so in this section, we're going to be covering alkyl halide synthesis, and you probably remember alkyl halides from organic one, right? An alkyl halide is basically, if I just had to come up with a generic one, right? This is the alkyl part, and then this would be the halide part, right? So it has an alkyl component to it, or carbon chain, and then it has a halogen as the halide part, right? So there are several ways to make alkyl halides. One way you learned in part one of organic is to do what's called a radical substitution. Do y'all remember this? Let me hold up. Let me put a heading up here so we can stay orderly. So the first way that you learned is radical substitution. Substitution. I hate this word. I always misspell it. How many of you remember this radical substitution reaction from part one? You shine light and you do either bromine or chlorine, right? And you end up with a bromine here, bromine here. Let's see. Yeah, those are the two products because it's symmetrical. Anybody remember that?
Mm-hmm.
Vaguely.
Vaguely.
Right. It was called radical substitution because in one of the steps you actually formed a radical. Does everybody know what a radical is? Anybody not know what that is? It's an atom with a single unpaired electron. Right, single unpaired electron. So if you, what are the three steps to a radical substitution? Anybody remember from part one? There was initiation, is that right? And then what are the other two steps? Think hard.
Propagation.
Who was that?
Brianna.
In termination.
Yeah,
Good.
termination.
Propagation. And then termination. Right, so in initiation, that's when you create your reactive radical, right? You shine light on bromine in this case. You break the bond. Anybody remember what type of cleavage that is? Bond cleavage?
What are those on top of the arrows? What is that again?
Fish hooks. It's a half arrow.
That's right.
Because that means you're moving one electron. Is that right?
Mm-hmm.
So you break up bromine. I'm gonna erase the termination so I can have more room. And then in propagation, let's just say we're gonna pull off one of these hydrogens. I'm not gonna show the whole mechanism. Right, in propagation, you pull off a hydrogen from one of the carbons. That process is called abstraction. Right, and then you make a new radical. Right, now you have an unpaired electron there plus HBr. I'm only gonna go through the steps for that side. Is this coming back to anybody? Did y'all cover this? If you took Abdallah, I know we covered it in my class.
I think so. Can't really remember.
You know what chapter it was off the top of your head?
No, I don't.
Okay.
In the old book, I think it was chapter 6, but I'm not sure what chapter it was in. in the new book.
Okay.
But I do have a bunch of I have a bunch of videos that I made on it for part 1. I think I'll send out one of those when I send out the the video for Allylic Bromination. All right. So you break that CH bond, you end up with a radical, and then in termination, what happens? What does terminate mean in a literal sense?
Like eliminate.
It's the end, right? So the goal was to make an alkyl halide. So I take the two radicals and I'm going to combine them. Uh-oh. Right, so that's one of the products. I didn't show the other one, but it's the same exact mechanism, just it happens on a different carbon. So you have initiation, propagation, and then termination. That's what happens in a radical substitution. That's one way to make alkyl halides. What's another way? Anybody remember? If you started with an alkene. Right, if we add HX to an alkene, so we take a double bond like this and add like HCl to it, and we end up with an alkyl halide, right, where the H adds to one side and the chlorine adds to the other side. We just talked about this, right, on carbon-to-carbon addition. So that's the second method. The method that we're going to talk about today, it kind of pulls on radical substitution, right? But it's a little bit different start material. So we're going to learn a couple of these methods. We're going to learn allylic bromination. Right, and so this is a and I'm going to explain what all the reagents are and all that stuff. So you need, in order to do allylic bromination, you need MBS, which I'll show you what that is in a minute, and then light. So allylic bromination is also a radical process. It goes through a radical mechanism. Right, at this carbon right here, that's your allylic site. Right, allylic simply means that it's adjacent to a double bond. Can you see that? So the double bond is here, and then the carbon next door to it, which would be this carbon right here, that's what we call the allylic site. Is that all right so far?
Yes.
All right. So I'm gonna show you the products, and then we're gonna go through the mechanism for this. And then there's a handout that I'm gonna pull up that we'll start working through, and I made it available on Blackboard too, so you can.
Is it the one you just posted?
Yes, I think it's called Allylic Bromination Assignment 1 or something like that. You got an announcement for that?
Yes.
Oh, that's cool. I'm glad you said that, because now I don't feel weird for not sending out an announcement about it. All right. So let's look at what the two products are going to look like, because you're going to get two products, right? And I'll explain why. So can I erase this stuff right here, the allylic stuff, so I can just write the products down there?
Yeah, you can.
All right. So one of my products is going to look like this, where bromine is right there on that site. My other product is going to look like this, where bromine is here. And all of that is, so to be that plus that, to be those two products. Right, there's a reason for that. We're going to talk about that when we get to the mechanism. All right, so that's allylic bromination in a nutshell. And as a rule of thumb, I'm gonna give you this information to help you understand that why you see two products. But then when we get to the question that we're going to answer, then I'll explain it more. So every allylic radical is going to be is going to rearrange through resonance.
Is that just a rule?
Mm-hmm. Right. There's a reason why this site is preferred over the other sites, and I'll explain that. My phone keep buzzing. I know I'm in class. Let me be. All right. 1 second. I gotta print something out real quick. All right, so that's one method. That's a third method. Another method that we're gonna look at, and then before we jump to this handout, there's one other method I want to tell you about, and then we're gonna start working on some allylic bromination questions. So the fourth method is conversion of alcohols into alkyl halides. All right. So you'll see this abbreviated as this, like ROH plus, I always like to say ZX, where X is my halogen. And then that's gonna basically substitute the OH with the X. So you end up with RX plus ZOH. Right, so it's a substitution. Right, so those are the two methods, the last two methods that we talked about. Those are going to be the methods that we're going to dive into. All right, any questions about anything so far?
So there's 4 methods.
Yeah, but the ones we're concerned about are, for the purposes of the test, will be 3 and 4.
Oh, just allylic bromination
Mm-hmm. And
and
alcohols to alkyl halides.
Right.
You got it? Okay.
I'm writing this down.
Okay. Yeah, take your time. All right, so alcohols, the alkyl halides, and then allylic bromination, that's where we're going to put our focus.
All right, I'm okay.
All right. So let's jump out of here and jump on this handout, and then we're going to go through the mechanism and explain everything and all that stuff. All right. So here's the first question. It says draw all possible products for reaction 1 and propose a mechanism for their formation. All right, so here's the thing to think about. Anytime anytime you're doing an allylic bromination problem, right? That's what we're looking at. You look at, this is the giveaway, the MBS and light, that's the giveaway that it's allylic bromination. Those reagents are specific. The MBS is a specific reagent for allylic bromination, right? And so what you have to think about now, here's the other part of that. So look for MBS, right? That's specific for allylic bromination. The second part is, where are my allylic sites on here? In reaction 1. On this substrate, where are my
That
allylic sites?
tertiary bond right there.
Okay, right here. You say right here?
Yeah.
Okay, good. And where's the other one?
The CH3 on the end.
Right here. Great.
Yeah.
So those are my 2 allylic sites.
Dr. Russell,
Yes.
what makes it an allylic site?
It's adjacent to a double bond.
Adjacent, right.
So here's the double bond right here, right?
Okay.
So the 2 carbons that are next door to it are allylic. Does that make sense?
Yes, thank you.
Okay, great. So now let's think about it. If we got 2 allylic sites, the other part to helping you solve these questions or solve these problems is to understand that if you have an allylic site on a structure and it's not symmetrical, it's going to do resonance and rearrange, right? The radical that you get in propagation is going to rearrange. So for every allylic site you have, you're going to get 2 products. Are you following that?
Oh, okay.
So how many products do we, so let me write that down somewhere. So,
Yeah, please. Get 2.
so allylic rearrangement will result in 2 times products. Right, so if you
So
got
there's 2 allylic sites, you're gonna have 2 products?
2 times that.
Oh,
4.
so 4.
Yeah, so if you got 2 sites, you'll have 4 products. If you got 4 sites, then you'll have 8 products, so on and so forth. Right, because each allylic radical that you get in propagation can rearrange. Right, so you're gonna basically get 2 products for each site. So if you got 1 allylic site, you get 2 products. If you got 2 sites, you'll get 4 products, so on and so forth. When we get to the mechanism, you'll see why that's the case. All right, so with MBS and then light and a allylic substrate, you know you're going to be doing allylic bromination. So but the rearrangement of the radical that you get in propagation always is going to always give you more than 1 product. So you'll get 2 times the products. Is that making sense?
Mm-hmm. You're always gonna have more than 1.
Yes. Unless unless the radical that you make can't rearrange, then you'll only get 1 product. All right. So let's look at this one. Let me just draw the products out first.
You can erase this stuff. I don't know if anyone wrote it down.
Oh, I will. So that's 1 product. Are we okay with that?
Wait.
Because it's allylic bromination, right? So we're putting a bromine at the allylic site. So at this allylic site right here, I'm going to add a bromine.
Oh, I see.
Should I put the CH3s back in? Make that out.
Yes, I see.
Is that okay? That's 1 of my products.
Mm-hmm.
What's the other one? Right off the break, without even thinking about rearrangement or all that stuff. What's the other one?
The bromine's gonna be
bromine to the CH3.
I'm gonna put a bromine on that side, right? Keep in
double
mind.
bond away?
Say again.
Is the double bond going to go away?
No. The double bond doesn't go away because you're not adding to that. You're only adding to the allylic site. So the second product is going to look like this.
Oh, I see. Okay.
Come on, man. So that stays, and then down here you're going to have a bromine on that carbon. Now keep in mind this is a CH2 now.
Mm-hmm.
Right.
Go ahead.
think someone was just agreeing with you.
Yeah, because I had to take off a hydrogen to put on bromine.
Mm-hmm.
Oh.
Which is gonna be 2.
Otherwise, that carbon will have 5 bonds to it.
Okay.
Okay.
Is that okay?
Oh,
Yes.
Yes.
All right, now let me show you what the other 2 products look like, and then we're gonna go step by step through the mechanism. So this is gonna be one of my products. That's one of them. All right,
Could you
don't
bring
panic.
the picture down a little bit?
The same question or this
Yeah,
is
it's for the same question, yes.
Oh, I was finna say.
Is that better? Can you see it now, all of
Yes.
them?
Yes.
So that's one. Don't panic. I know it looks weird, but I'm gonna show you exactly where it comes from. All right.
Mm-hmm.
And then here's so I'm put a plus sign here because all of these products are possible. The other one is gonna look like this. Oh, that's ugly. Sorry. It's gonna look like that. That's my 4th product. And we're gonna go through the mechanism step by step and see how each one of those products got formed. So when this reaction reaches the termination stage, these are the 4 radicals. Well, these are the 4 products that I'm going to get. Go ahead. Somebody was getting ready to ask a question.
This is before it reaches the termination.
No. All the products come from termination.
Oh, okay.
But we have to show how we get to the termination step. Okay. Is that good? We're good so far? Don't panic yet. It's Monday. No panicking on Monday. All right. So let's go down here to where we're going to show the mechanism. I'm going to show you what MBS looks like. I don't expect you to remember it. And yeah, I don't expect you to remember. You'll never have to, you won't have to remember it on the test because it'll probably be given to you. So this is going to be my initiation step. All right. So MBS looks like this. This is N bromo succinimide. N bromo succinimide. That's bad. Hold up. You know, handwriting was the only class in elementary school I got a bad grade in.
Oh, not a big.
Well, I got a C.
No.
It kept me off the honor roll. My mama came and cussed everybody out. And then they put me back on the honor roll. I had all A's in the C in handwriting.
Jeez. They could have just gave you a B.
Nah, I wasn't worried about it. My handwriting it's legendary. It's always been bad. Well, anyway, so this is MBS, and I'm going to shine light on it.
Mm-hmm.
What do you think is going to happen? What happens when you shine light on a bond?
It's gonna rotate.
break.
You break it.
Oh.
Anybody remember the type of cleavage that happens when you shine light on a bond? It's not polar, it's radical. Anybody remember this term from part 1, homolytic?
Yes.
I didn't get a lot of nothing on that one. Homo meaning same, lytic meaning to cut, right? So each one of those.
Oh, I didn't even, yeah, I remember that.
Yeah. Good. All right. So each one of those is gonna each electron in the bond ends up with one of the atoms that makes up that bond. So I'm left with this, the radical here, and then this. Everybody okay with that? All I did was break the AMBR bond.
Yes.
All right. Now here's a question that's going to come up. when we get to the propagation part, right? Well, the termination part, we got 4 products, so we're gonna need 4 bromines. Although you only see 1 bromine here in the initiation step, keep in mind, if I'm using 1 mole of MBS, that's Avogadro's number of molecules, right? So I'll never run out of bromine. Are you following that?
You said we're never gonna run out of bromine.
No, because what I'm saying is when we get to termination, you're going to see 4 radicals that we're going to terminate. But then you're going to think back to this first part and say, wait a minute, we only made 1 bromine radical. You're making billions of those, right? Because if I start with 1 mole of MBS, isn't 1 mole Avogadro's number of molecules per mole?
Mm-hmm.
Right. So you'll never run out of bromine. That's the point. You'll see what I mean when we get to the termination part. We okay so far?
We're okay.
All right.
Yes.
Take a deep breath. It's Monday. So propagation is the next step. All right. So let me go back and make sure I draw the right compound. All right. So I'm going to start. I'm going to start here. Right. And then put these 2 CH3s back. All right, so on propagation, that's when I go through and abstract hydrogen from the chain. Right? How does that happen? Anybody remember from part 1? So I'm going to break this CH bond right here. Are you following?
Yes.
The way I
Yes.
break it is it's a homolytic cleavage. So one electron is going to go, let me change colors here. 1 electron is going to go here to that carbon, and then 1 is coming here with hydrogen. And it's bromine that's kind of facilitating that. Right? So what ends up happening is the bromine and the hydrogen end up together, right? In a bond, a covalent bond. That's what those 2 arrows kind of meeting together means. All right. So that radical that I get from that looks like this. Is that okay?
What's that little dot right there? That's supposed to be a
That's an electron
electron.
on that carbon, on this carbon right here,
Mm-hmm.
right? Because I just broke the carbon hydrogen bond on the other side.
Okay, gotcha.
All right, we cool so far? Let me ask you this: so that allylic radical, what can it do? Like radicals are not stable. So what's one way to stabilize either a lone pair of electrons or a plus charge or a minus charge? What's one way to stabilize that?
What's the question?
That radical is not stable like it is,
Mhm.
but there's a way to stabilize it. What would you do? Think back to that first, maybe second week in organic 1.
You feel
I want to
the
say
upgrade or
resonance.
something?
Say again.
I was gonna say resonance.
Who said that?
Natalie.
You're right. That's how we stabilize charges, lone pairs, radicals by resonance. What's the criteria for doing resonance? I'm just refreshing you. This is not a part of this class because resonance was probably pounded into you in part 1. At least it should have been. But what's the criteria for resonance? You got to have a what? A donor,
And a
acceptor,
acceptor.
adjacent to one another, right?
Right.
Yeah, you're rearranging to
Right.
find
So
stability.
remember how we said up top that the radicals can rearrange, and that's how you get these other products. So that's what's going to happen. That happens during propagation. Right. So let me show you what happens, and then let's see if we can make this make sense. So here's this is what we call an allylic radical. Right. It's an allylic radical. So here's the donor acceptor unit. So the alkene right here is right next door to this carbon that has a radical that has one unpaired electron on it. Right. So there's a way that I can rearrange that. If I take one electron from the pi bond, I got to zoom in so I can make sure I write this so you can see the arrows. Can y'all still see that structure?
Mm-hmm.
All right, I'm going to take one electron from here. I'm going to take this electron, dang it, and move it here. You following? Do you see what just happened?
You're moving the electrons.
Yeah, but what I'm also doing in the process is I'm going to end up shifting this pi bond to here. Right? Because it takes 2 electrons to make a bond. Is that right?
Mm-hmm.
Mhm.
So if I take one from the pi bond and one from that radical, and look where the arrows are stopping. They're stopping on the sigma bond. Right? So that means
Right.
I'm going to take those 2 electrons and move them there to make a new pi bond. And then I'm going to take the other electron in the pi bond and move it to this carbon right here. Every allylic radical is going to rearrange the same way. Right? We're going to go, I got some examples on this handout. We're going to, after we get finished with this, we're going to walk through those. All right. What should I get from that?
Would the radical
The radical,
move or
go ahead.
disappear? Would the radical move or disappear?
It's not going to disappear. It's going to shift over.
Okay. So it would shift over to where the original pi bond is?
No, let me draw the new structure and then you'll see what happened. Come on, you stupid thing. That's what a new radical is going to be. Look at the arrows up top and follow that. So this arrow and this arrow both say that I'm making a pi bond here. Right?
Yeah, so the radical shifted to where the original one was.
Right. So that's going to be a new pi bond. And then the other arrow here says that I'm going to make a new radical.
Yeah, I don't think we ever went over this in a college class.
At all.
Y'all didn't go over
No,
y'all didn't go over resonance with radicals?
no.
No.
Yeah, resonance.
I remember with radical.
It wasn't
Yeah,
even
but
that
we
deep.
don't run-
Man, I ain't heard that many people talk since the first day of class.
Oh,
Bro, no, bro, nah, we do that, bro, no. That's all right. We'll walk it down. There's no rush. We'll walk this down. I got some examples we can do. But are you following like let me do this. Let me go to here because I think they're right back here. All right, hold up. Let's do this. So look at the top structure. Can y'all see that? I need to zoom so my
Yes.
highlight won't look like crap. Do you see that?
Yes.
What do you notice about it? You see how these 3 atoms here are
It's in an allylic position.
It's an allylic radical, isn't it?
Yeah.
That means that,
Mhm.
let me explain what that means. So here's allylic, here's an allylic carbon, right? If there's a radical, it's sitting in a p orbital. There's one electron in there, and then these p orbitals right here also have one electron in them, right? And so
Mhm.
what happens is the radical, you see how the three orbitals are lined up right next to each other?
Mhm.
That means they can talk to each other,
Yes.
right? If that radical was one carbon away like that, they couldn't talk, right?
Okay.
Because the orbitals can't overlap. But
Okay.
those orbitals are able to overlap, that means they can share electrons.
So that one with the lone pair is included with the allylic
Yeah,
because it has a
yeah,
lone
because
pair.
it's right next door to it. It's not a lone pair though, it's a radical. A lone pair will be an actual pair, right? It'll be two electrons.
Okay.
All right. So the fact that those orbitals are adjacent like that and they can talk, that means you can share electrons among them. What that means, if y'all remember when you did resonance, there's a specific reason for doing resonance, right? Resonance and delocalizes electrons or charge. Right? What that term means, delocalize, is exactly what it sounds like. It takes the charge or the electrons off of one atom and you're able to share it or spread it out over other atoms. Does that make sense? And that by doing that, you're able to stabilize that structure, that molecule. So it's either going to be a charge or an electron that you can delocalize. So this allylic radical is one of about 5 patterns that you can look for in order to determine whether or not resonance is possible. All right. So let's look at what should happen. How would you rearrange this radical right here? What would you do?
Would you move it next to the double bond?
You want to move it to here?
Yeah, I think so.
Yeah. And then you can take one from here and put it there, right? What does that mean? What does that mean? It means you're going to end up with a new pi bond right here, right?
Mhm.
And then the third is always the same 3 arrows too, by the way. It never changes. The third arrow is going to go here. Notice where I put it. See how I pointed that arrow at the vertex? At that
Right.
carbon? That means that's where that electron is going to be.
Okay. And it's the electron
Okay.
from the pi bond, right?
Yes, the
Okay.
second one. The first one is moving to make a new pi bond,
Okay.
right? So the new structure is going to look like this. Not like that. Right? Where the methyl group is still out here. The double bond is now here. And this is
Radicals at the
come on, Russell. The other electron is going to be up here.
right.
I need a stylus. That's what I need. Too cheap to
Yeah.
buy one. I'm too cheap to buy one.
They're like $25
I got
on Amazon.
I got 2 teenagers I'm raising. They eat a lot, so I'll just keep using my finger. It's cool. Is that okay? Are y'all following that?
Yeah.
So it's a pattern. In order, I'm gonna send y'all this resonance video too, to refresh you, because all you're doing is looking for certain patterns. If the pattern is there, then you can do resonance. If it's not there, you can't. It's that simple. So I'm gonna send that to y'all after class. That and a little Bromination video.
So
And is that the only form? Just this
That's
one?
it.
since we
That's it.
have 3 allylics, wouldn't it be 6 ways to do it? Or is that
You only have one allylic radical in this case, right? You see where that unpaired electron is right there?
Yeah.
Erase all these other dots. So this electron right here, so that means you're only going to be able to shift that one time. The only way to go now is backwards, to go here.
But we
Right.
have 3 allylic sites. I'm confused.
No, you only got 2 allylic sites. But you can't, so this is allylic also, but there's no electron there. You follow what I'm saying? You can only rearrange the allylic radical. You can't just rearrange the site because it's there. There has got to be an electron there for you to do that to do resonance.
So then
I
how
think-
did you do the last question?
I think they're thinking about bromination
We
and
had
the
electrons there. You see that? We pulled off the hydrogen right here. Is that right? And then
Yeah.
over here, let me take the arrows out. Over here, we had an electron, and then we shifted it here, right? And then we had a pi bond next door to it. So we took one electron from that pi bond and shifted it here. Just like we just did on that example. Right? We didn't really touch the other allylic site. Yes or no?
Kind of.
Right? You can only rearrange it if there's an electron there.
I think they're getting confused with because the first part that we were doing was a reaction, whereas what we're doing now is just doing
An
resonance.
example of resonance, yes.
Yeah, so it's completely different things. It's just rearranging.
Yeah, I'm just showing you how those radicals can rearrange through resonance. All right. Let's go back to here, to the propagation step. So that's one propagation step. What do you think the other propagation step? Where is that going to happen? Where's the other allylic site?
On the CH3 at the end.
Right here.
Yeah.
So that's where my other propagation step is going to happen. Let me see if I can draw that without. So I'm going to draw the hydrogens out on that. All right. So what's going to happen in this propagation step? What happened in the top propagation step? Did
You would
did
get
bromine pull off
yeah, the hydrogen.
an allylic hydrogen?
Yeah.
So it's going to do the same thing on the other side. All right, it's going to do the same thing over here. Right, so I'm going to take this arrow and put it here because I'm breaking that CH bond. And then the other electron in the CH bond, I'm giving it to carbon. Yes or no?
Do you have to draw the 3 arrows like that? 'Cause
Yes.
I've just never seen
Because
that.
it's homolytic.
Okay.
So the bond is breaking. Let me show you here. The bond is going to break here and here. Right?
Okay.
Now, if you want to put the other arrow on the other side, like, not like that, I had to curve it back some more. Like that, that's fine too. But you have to show that one electron going back to carbon. That's how you form that radical.
Gotcha.
And then bromine is what's doing the abstraction. So I have to show an arrow coming from there too. Yes or no?
Yes.
So remember, if you got two allylic sites, then abstraction is going to happen at both of those sites. Right? So what do we get from that? What's that radical going to look like?
You'd have a radical at the very end.
It's going to be right where I pull that electron off from, and it's going to be right
Yeah.
here. I'll put the hydrogens back in too. You're going to have a radical right there. Is that right?
Mm-hmm.
Plus what?
The brom.
Plus,
Yeah, hydrogen.
Plus HBr. Now, you got a radical right there. What's going to happen to it?
you would have to rearrange it.
It's going to do resonance, right?
Yeah.
If resonance is possible,
Right.
it's going to happen. Right? So somebody help me out. What are the arrows going to look like?
So you would move the radical into the sigma bond next to it. And
Like
then,
that?
Yep. And then same thing with the pi bond, you would put it to the sigma bond next to it.
Mm-hmm.
And then also draw another arrow from this pi bond to the, yep.
Like that. Do you see how it's three arrows, just like it was when you pluck that hydrogen off?
Mm-hmm.
It's a pattern, and it doesn't change. If you got an allylic radical, it's going to do the exact same thing every single time. Where's my new pi bond going to be now?
Right next to the carbon.
Next to the
Right, it's going to be right here, isn't it? Let me see if I can change the color. It's going to be here, isn't it? Is
Yes.
that right?
right.
Yes.
All right.
Yeah.
So I'm going to see if I can fit it in down here. So now my resin after rearrangement, this is going to look like this. So that's still CH2. And then here, all that's still the same. And then my radical is right there.
Right.
Is that right?
Yeah.
So how many radicals did I make in propagation? Total. I made 4, didn't I? I made this one. And then the resonance form of that. And then I made this one and the resonance form of that. Are you following that?
Yes.
So I made a total of 4 radicals. So when you look at the products, can you see now where those other products came from?
Yes.
Right, they came from the resonance forms, didn't they? These 2 products right here. Is that okay?
A little more.
So what, instead of the radical moving, was it the BR that was moving?
No. It was the electron that was moving. What happens is, okay, so there's no bromine associated with this step other than doing the abstraction, pulling off hydrogen. Are you following?
Mm-hmm.
Okay.
So in order to get to my products, again, that's where that final step comes in, that termination step.
Okay.
So all of the radicals that you made up there, let me draw them out again. Shrink it down so I can see them all. So I made this one. I'm just going to leave the CH3s off just. So I made that radical. Is that right?
Mm-hmm.
I made this radical. Where the electrons on that end. On a CH2. Is that right?
Right.
And then I made this radical. Come on, man. Where the electron is here. And then I made this radical. Where the electron is there. That looks more like a negative charge. Right? So those 4 radicals I'm going to combine with Br. That's what happens in termination. And it's a Br radical in each case. That's why I was saying, like, when you do the initiation step, don't get stuck on thinking you're only making 1 bromine. Right?
Okay, I got you.
Okay.
You're making billions of them. So it's enough of them to do abstraction, and there's enough of them to come back and finish up and do termination. Are y'all following that? The termination part? So it's initiation, propagation, and then termination. And so
Okay.
now what happens in termination?
BR is gonna bind.
You start pairing these things up, right?
Right.
I always say that this is the time, this is the part of the night when they turn the lights on at the club and you're trying to find somebody to go to Waffle House with. So boom, now so the 2 top BR and that radical get together. And then the same thing here. Right, let me erase that line right there. So this BR is gonna combine with that radical. And then here, same thing. And then here, same thing. Right? And that's where your products come from. Your products always come out of termination. Is that okay? Anybody got any questions? I'm sure this is like not really sticking right this moment, but it will by the time we look at it again on Wednesday, or actually when you look at it again in a minute, it'll stick.
Yeah, and just to confirm, there's going to be 3 topics for the exam, or how many?
Well, we'll do it with the chirality is 1, and then alkyl halides, synthesis of alkyl halides is the second. But we're not gonna. There's a yeah. So it'll be 2 topics.
Okay.
Yeah.
Okay.
I
We're
was
not going
gonna
into
make
the use of them. The use of
No,
alcohol
no, we're not
halides?
gonna have time. We'll
Okay.
start that. That part will be on the second exam.
Okay, just want to make sure so when I go back and revisit it and study it and all that.
Yeah, the application part we'll do for the second test, and we'll do more of this on Wednesday too. So don't panic.
So then the exam is gonna be over the first 2 things we was already doing.
Yes.
Okay.
Is this the worksheet that you posted for this? Is that going to be due on Friday as well?
Yes.
Okay.
We'll finish it. I promise.
Okay.
We really like only have one other example on here, and then the resonance stuff at the bottom. So we're almost done with it. But keep in mind, we're having class Wednesday and Friday, so don't panic.
Okay.
Now, it's not going to just be like no class. If the test is not, if it's on Blackboard and you got all weekend to do it, we're going to still have class Wednesday and Friday. So don't sweat it.
Okay.
All right. Any other questions?
Not at the moment.
All right. What I'm going to do is I can get this thing to come back. There we go. What I'm going to do is I'll send you, I'm going to upload this video to YouTube right quick. And then I'll send you a resonance video, a radical substitution video, and then an allylic bromination video. I'm going to send that to you like as soon as we get off.
Perfect.
Because the
Okay.
resonance will just be to refresh you. All right. Any questions about anything? So I'm gonna stop recording, stop the meeting. And
Actually, I have a question,
go ahead.
but it's not about what we just said. It's about on the quiz with the S and the R.
Mhm.
I kind of messed up, but like I thought we said when H is horizontal, it automatically becomes S, right? No, automatically becomes R. Yeah, it comes R. It becomes R, right?
No, it
No.
depends on what the priorities are of the groups. If they're oriented, if you're talking about for a Fisher projection, right?
Yes.
So if the groups are oriented in a clockwise fashion, but the hydrogen is horizontal on that Fisher projection, then you reverse the configuration. So clockwise is R, but because H is horizontal, you reverse it and call it S, and vice versa. If the groups are oriented in a counterclockwise fashion, right? So they're going when you prioritize them and you count them, and you counting counterclockwise. If H is horizontal, even though it's S in the way that the groups are prioritized and arranged, you call it R.
And that's for everything when it comes to Fisher
Fisher
projection with the
yeah.
hydrogen with the
Yeah,
H.
not everything.
Okay. Thank you.
All right. All right. Any other questions about anything? If not, I'm going to go ahead and end the video so I can get all this stuff to you real quick before my next class.
Okay, have a good day.
All right. Thank y'all.